What's up, guys? Yeah, so today I want to discuss the birthday paradox. But I try to do is that I will try to prove the asymptotics and so give some quantitative results and estimate the probability. Okay, so but the main theorem that I want to prove here is that is the following. Okay, so let's say we get n balls. Okay, so we put n balls into m and let's say m bins or m box 6. So our condition must be m greater or equal to n. Okay, and so there are two cases. The first, there are two different cases. Whether boxes are the same or not. So whether so let's I will explain in detail. So whether box is the same. And the results is the same. So the probability of there's no collision. Okay, so no collision means that no two balls put into same box goes to 0 as n goes to infinity if m is greater than order of n squared. Okay, so what this means is that suppose you choose m to be, let's say you choose m to be constant times n to the cube, then the probability will respect to n will go to 0 as n goes to infinity. Sorry, it's goes to 1. Sorry, I'm stupid because this is no collision, so collision will goes to 0. So that means if you take m to be large enough, then there will be, if you take m to be large enough, then the highly probabilities there will be no collision. Okay. Okay. So let's work on the first case. So proof. So first case is that let's say two boxes. So every box is different. Okay. So what I mean is that let's say I get x1, x2, which is xm. So I get xm boxes, which they satisfy this. Okay. And so I want to ask. So the probability of there is no collision will be the number of solution which restricted to each xi must be 0, 1, right? So it's number of solutions, right? But restricted to the each xi must be 0 or 1 divided by all the number of solutions. Okay, so the first one will be simple, right? For you choose m, there are m boxes, so you choose n of them, which you put ball in. So it's m choose n, and the second one is the famous results. I think it's, you can easily prove by combinatorics or using the Hardy-Littlewood circle method. Okay, so basically it is this. Okay, so we want to claim. So our goal is to claim if somebody choose m to be greater than O(n) cube, or O(n) squared, then it would be then this guy will be 1. Okay, so this is our proof, right? So we want to prove that if you choose the box large enough, then the probability of no collision will be 1. Okay, so now it's a simple now it's the simple mathematics that you try to check whether your asymptotics is very good. Okay, so let's do this. So this is n factorial, n minus n factorial, n plus n minus 1 factorial, n factorial, and n minus 1 factorial. So you get n factorial, and n minus n factorial, and n minus 1 factorial, n plus n minus 1 factorial. Okay, so let's write this. So let me just use this, right? So I can cancel this. I start from n minus n plus 1, n minus n plus 2, up to I think n minus n plus up to like n plus 1. Okay, because right. So this difference will start from n minus sorry, the final should be m. Okay. Okay, divided by, let's say, these two, right? So you start from m plus 1 up to m plus n minus 1. Okay, so you can easily write this as 1 minus m minus 1, the first term. And the second term can be written as 1 minus m plus 1 minus 1. Keep going, and then you get 1 minus m plus n minus 1. Okay, so final one should be also be n minus 1. Okay, so you got this. So this is our probabilities. Okay, so our goal is to bound this, right? Bound this. Okay, so let's quickly, let me just maybe quickly go through the detail. Okay, so I think bound list is not difficult. So can I copy this? Oh, let me just try to. Sorry, I'm stupid. Okay, it's fine. That okay. Yeah. So let me just start from here and try to approximate this guy. Okay, so to approximate this guy is not difficult. Okay. Okay, so all we need to do is just compute this guy, right? So we need just use the very simple inequality. Let's say 1 minus x1, 1 minus x2. So let's say x1, x2 are both these. Okay, so this guy is greater. It's just 1 minus x1, x2, right? Minus x1 plus this. So it's greater than 1 minus x1 minus x2. Okay, so for this one, which is greater than or equal to 1 minus m, and the sum over all these, right? So okay. So first I can replace this m plus 1 into m, right? So I can all replace m, and the sum over all these n minus 1 term. So I get n minus 1, which times n, right? Total should be n tenths. Okay, and so this is greater or equal to 1 minus n squared divided by n. Okay, so which prove our results. Okay, so because what we prove is that our probability of no collision is greater or equal to 1 minus n squared divided by n. So if I choose m to be greater than O squared term, then I get, let's say m is a let's for example, let's say m is n c n q, then this term will goes to 1 as n goes to infinity. Okay, so this is the first proof. Okay, so the second one, which is very interesting, is that what we're gonna do is that we use we do the usual birthday paradox. Okay, so the usual birthday paradox is that all the boxes are the same. Okay, so what it means that there's still m of them. Then you get n both. Okay, so you need to compute no collision. Okay, so it's the first one. The first ball you put into the ball, right? You put in the box. So the first ball are very lucky, right? He can go anywhere, so it's 1. But second ball cannot go to the box, which already in, right? So its probability is that 1 minus 1 over m, and the second ball cannot go to the first 2, right? So it's 1, 2 over m. Okay, so let's keep going. Okay, so you can see there's this is different from the first birthday paradox because somehow it solves the different problems, right? But solve a little bit different problem. Okay, so this is just m to the m, so m to the n, so m to the n, and the m minus 1 up to m minus n plus 1. Okay. Okay, and then we want to prove the same thing. We want to say that, oh, if m is larger than O n squared, then it should be 1 as n goes to infinity. Okay, so this is your interesting results. Okay, so let's denote this by P and N. Okay. Okay, so the first fact that we can use is this. So exponential x minus negative x greater or equal to 1 minus x for every x greater or equal to 0. Okay, so this is, so you can use to bound this P and N. Okay, but this is upper bound, which is not we want, right? Because we can bound it. Okay, so we can just bound this by using it by taking the exponential. So this is minus exponential 0, exponential 1 minus 1 over m, exponential minus 2 over m, exponential minus n minus 1 over m. Okay, so this is the 0 plus 1 up to n minus 1, which is exponential minus m, and n minus 1 divided by 2, which is exponential negative n minus 1 divided by 2a. Okay, so this is the upper bound. Okay. So the next things we want to get is the lower bound. Actually, the lower bound is just what we want, right? Because we want lower bounds. Means that so we want lower bound, right? And suppose n goes to infinity, lower bound go to 1, then we know the answer should be 1. Okay. Okay, so another fact that we need to use is that 1 minus epsilon is actually greater or equal to exponential minus epsilon minus c epsilon squared. Okay, so there is the c greater than 0, and for all 0 less than epsilon less than 1. Okay, so this is somehow like the results, some results that that one can use. Okay, and then, I mean you can easily prove this, right? Because if you do the tidal expansion, then in this place that there will be second square term, but this is only a linear term left hand side. So if you do the tidal expansion, then you can easily see this is true. Okay, so our PNN greater or equal to exponential negative, let's say c. So these terms will give me the same term, right? So I only need to consider this exponential minus c epsilon square term. Okay, so I can get something which is exactly the same as what I did. And then for these terms, I get the 1 over m squared of the 1 over n minus 1 squared. Okay, so our P and N contains some lower bound, which there is constant C. M squared, 1 squared plus 2 squared up to n minus 1 squared. Okay, so this is a famous result, which is O cube. Okay, so I think you can easily prove. Okay, this. Okay, so your P and M can be written as minus exponential negative n squared divided by 2m, exponential n divided by 2m, and exponential negative cm squared all to the n cube. Okay, so now I can do the entire expansion, right? I can say this guy is greater or equal to exponential negative n squared divided by 2m. Now I expand this. So this guy is basically 1 plus O n divided by 2m, 1 minus c m cube O to the n cube. Okay, so now we got 2 error terms. Okay, so now I get the answer, right? Because now I want to prove, I can easily prove our results. I just choose, let's say O m is greater than O n cube. Okay, so if m is greater than O n cube, these terms are negligible, right? These terms negligible, and these terms is 1, right? Because now I get since m is larger than O n cube. Okay. Right, this m is larger than O n cube. Okay, so this term will be exponential negative 0, which is 1, and then this term is negligible because m is O n cube, and then this is also right since n cube divided by m cube. Okay, so you can check the. So let's do something, right? So we get 2 error terms, the first error term, and then the second error term is this. Okay, and then you can check whether they are equal when they are equal. So you get n divided by 2m is n cubed divided by n cubed divided by m squared. So you get n squared equal to m. So you can say when m equals to n squared, that you get something non-trivial here. But when m greater than O n cube, then definitely, sorry, it's big O, then definitely you get 1. Okay. So when you get 1, as n goes to infinity. Okay, so this is like 2 different versions of birthday paradox, and but they both give you the same results. That if you choose m to be larger than the quadratic of the number of balls, then you always get 1 probability. Okay, so see you guys next video.